of integration by parts, definite integral and some of its properties, and the integration of marginal functions and their particular solution. So as we know that we have integrated using the basic rules that we discussed before. If we have a function under the integral with any power with its derivative, we know that this differential is going to be f of n plus 1 over n plus 1. We update the power if the power is not equal to -1, right? And if the power is equal to -1, we update it as the ln or the ln of the absolute of the function plus c. So it's either this or that. And then we have the integration of the exponential. So if we have the integration of the e to the power of x, that was the natural exponential, its integration is itself, and its derivative was itself as well. And if we have the integration of e to the power of any function, its derivative should exist, or we should have prepared it in order to solve the integral operator and say that that was the derivative of the e to the power of the function plus c. Okay, now what about the integration of the ln of x? If we have the function ln x under the integral, how can we solve this integral? Something else. What if we have the integration of x to the power of x? This is the product of two functions. If we thought about the derivative of the x, so the derivative of the x is 1, as we know, and the derivative of e to the power of x is e to the power of x, is the same function. So none of the two operands or the two these terms is the derivative of the other, right? So how can we do this? We will return back to the product rule of the derivative, u times v dash, or let's apply the d by dx. The derivative of the product of a function was the first derivative, the second, so the derivative of the dv by dx plus the second derivative, the first. Okay, and then they rewrote this formula using the u dv by dx. The u dv by dx will be equal, if you want to solve this equation for the u dv by dx times this product, we can take that term to the other side with its opposite sign. Yes, so it's going to be d by dx, the differential of the product u times v, and then minus the v du by dx. In order to solve it or to return back, we will apply the integral on the whole terms. So we will get the integral here, and then because we have two terms, we have the integral, we can apply the integral to the right side as a whole and then distribute it over the two terms minus that are subtracted. Okay, here we have an integration followed by differentiation with differential operator, and of course these are of opposite function, so they will cancel their function, and then we have here the integral of the u with the dv. Of course we add the dx while we add the integral, so we have dx here. So we will say that this is going to be rewritten as u times dv is equal to, these two operators will cancel each other and will leave us with the u times v minus the integration of v du. So the integration of u dv, which is a product of two functions, is equal to u times v minus the integration of v du. This is from where this formula came, and we will be able to use it now. Let's try to integrate this integral, simple one, which is x times e to the power of x. And by choosing one of the two functions, the x and the e to the power of x as u. So we will choose u as x and the dv as e to the power of x dx. So we have now divided the integral into a function x and e to the power of x dx. In order to solve it, if we call this xu and e to the power of x dx as dv, we need to say that the solution is u times v. We have u and we have the d of v, or the derivative of v, so we need to get v. And you remember, if we have a function and we applied the differentiation, the differential operator to this function, we get the derivative, the v and the v dash, or the f and f dash. And if you want to go back to the function, we apply the integral operator, right? So in order to get the v, we need to integrate the dv. And integrating the dv means that we will integrate the e to the power of x, and we know that its integral is the same function, e to the power of x. And in order to continue solving this technique, we need to say minus the integration of v that we have now times du, the derivative of u. So we need to differentiate u. Let's differentiate it below it. So the derivative of u is 1, and we differentiated with respect to x. Now we need to write this formula, so we will always use this technique to multiply this diagonal minus integration the horizontal. So u times v, or if we call that I, now that integral is equal to u, which is x, times v, which is now e to the power of x, minus the integration of this product, the product of these two, du times the v. So 1 times e to the power of x is e to the power of x dx. Now we have another integral, but take care that always this integral is going to be reduced. It's always going to be simpler than the original integration. The integration of e to the power of x, we can solve it directly because it's not a product. The integration is e to the power of x plus c. Now we are able, c is the integral constant, of course. Now we are able to differentiate or to integrate the product of two functions. Let's move to the worksheet, other problems from the worksheet, and take this exercise 1. So now solving. This is a similar integral in part A, like the one we solved before. So we will choose u as x and the dv as e to the power of 3x dx. And as we said that we need to differentiate u, so we will say u dash directly, its derivative is 1, and the v is the integration of the dv, so it's the integration of the e to the power of 3x dx. And we know that in this integration, this is a simple one where we need only the derivative of the function to be beside. So as if we multiply by 3, which is the derivative of the power, and cancel it outside the integral because it's a constant, it can go outside. And then the integration is going to be e to the power 3x over 3 like we did before. So this integral here is going to be e to the power 3x divided by 3, and then we will apply the formula u times v minus integration v du. So this integral is equal to x times e to the power of 3x by 3 minus integration of the product of u dash times e power 3x over 3. Now we have e to the power 3x over 3 dx. And you know that the constant can go outside the integration as it's a linear operator. So we have here x times e to the power 3x over 3 minus 1 over 3, and the integration of the e to the power 3x is e to the power 3x over 3, like we had here. And then now we are done with all of the integrations. Yes, so we will add the integral constant. And here we go. Let's go to part B, where we have the integral of the len raised to the power of 2x. Let's first integrate len dx, and then we move to the len to the power of 2. If we want to integrate len, we don't know the len is derivative what? Because we know that we need to get its antiderivative. So we think about the function inside the integral as a derivative of another function. So we imagine simply that the len x is multiplied by 1, and we take u as the len of x because we are able to differentiate it, and the dv we will take the 1 or simply the dx. Now this column, in this column we differentiate, so we will get u dash, which is du by dx. The derivative of len x, yes, is 1 over x. And the v here we integrate. In this column we integrate. So the v is going to be the integration of the dv. And this is going to be the integration of the dx, or the 1 times dx. The integration and the d goes, and we are dropped with x, or simply you can say 1 is the derivative of what? It's the derivative of x. And then we rewrite that with u times v minus the integration v du. So the integration is x times len x minus the integration of the product of these two terms, which is 1 over x times x dx. Now this 1 over x times the x can be simplified. We can simplify this, and we are left with x len x minus the integration of what? Of only 1 or of dx. So simply it's going to be x times len x as it was, minus the last integral, which is very simple, and equal to x, and then we will add plus c. So this is the integration of the len x. Now let's integrate the len power 2. This is number B, integrating the len power 2 of x dx. As we said, now that we don't know the len is the derivative of what, so we'll always solve this integral using the biparts technique, where we divide the function under the integral into two, u and dv, and then we are able to solve it as uv minus the integral of v du. So here we will use u as the len power of 2x, and the dv is going to be the dx, or 1. You may call it 1, of course. Now we need to differentiate. So let's differentiate u dash. Len to the power of 2. Remember the power when it's over the len? It means that it's len x all to the power of 2. So this is the general power rule. We will drop the power and update the power of the bracket to be 2 minus 1 times the derivative of what inside the bracket, which is 1 over x. And in order to obtain the v, we will integrate the dx, which is equal to x. Now simply, if this is I, let's call this I. Now this I here, we are in part B. Now this I is equal to u times v. So it's the len x power of 2 times x minus the integral of, minus this integration, the product, so the integral of 2 len x times 1 over x times x dx. We get the product of the last column together under the integral, the 2 len x times 1 over x times x. Now of course we should simplify and remove this x with the other one. This is times x and this is 1 over x, so it will be removed, and the integral is going to be, so here we took out the constant 2 and we are left with the integration of ln x, which we have just done. It needs to be integrated by parts as well, and we will copy the solution that we achieved here as x ln x minus x, and close the bracket and then plus c. And this is going to be the final solution of the integral. So integrate. Now we have the integration of ln x. We can do it roughly in the draft and then return back the solution and put it multiplied by the -2 in addition to the other part. And here we go with the final integral. Here we have the product of x power 4 times ln x power of 2. So again, these two functions, none of them is the derivative of the other or even close to. So we will have to use the by parts technique using the u. As we said that we don't know the integration of ln, so we can't ever choose it as the dv. So we will take the dv as x to the power of 4 dx. Now the derivative of u is, we drop the power, so it becomes 2 ln x with the new power, which is 1, times the derivative, which is 1 over x of the ln x, and dx. Now integrating to obtain the v, the other side is going to be the integration of x to the power of 4 dx, which is simply the power is not -1, so we add 1 to the power and divide. We don't add plus c because we know that we will use this to rewrite the integral. Now we will multiply the u times v minus the integration of the horizontal. So this integration is going to be equal to u times v, which is ln x all to the power of 2, times v, which is x to the power of 5 over 5. And then minus the integration of the product of these two, the v du. The v is x power 5 over 5 times the du, which is 2 ln of x times 1 over x dx. Now this function under the integral seems to be need some simplification. So let's simplify this x with that power and update it with 4. Also, this 5 is a constant. It can go outside the integral, right? So this is going to be the ln x to the power of 2. We can write it like this simply, and x to the power of 5 over 5. This is multiplied with that, minus the integration. Let's take the 1 over 5 outside the integral. And then we have inside, also we have the 2. So let's take out the 2 as well. This 2 to take it outside the integral as well. So we have now 2 over 5. And inside we have x to the power of 4 times the ln x dx. Now what about this new integral? Let's compare it with what we have. The problem itself was x to the power of 4 times ln x power 2. So now the integral is reduced. Yes, the power of ln, instead of power of 2, it became to the power of 1. But again here, we still have a product between two functions, x to the power of 4 times the ln of x. So we need to apply another by parts, right? And we have to save the u that we used in the first by parts. So we will use the u as now the ln x and the dv as the x to the power of 4. As we did before, we will differentiate the ln x to be 1 over x dx, or we can write u dash equal, and the v is the integration of the dv, which is the integration of x to the power of 4 dx. Now this integral, in the integration we add to the power if it's not -1 and divide by the new power. And then we use the formula to write it u times v minus the integration of the horizontal. So this integration, let's call it something else like I1 to differentiate between it and the integral that we have here. So I1 now is equal to u times v, which is x to the power of 5 over 5 times ln x, minus the new integration, which is 1 over x here, times x power 5 over 5 dx, right? So this is going to be x to the power of 5 over 5 times ln x minus, and inside the integration here we can simplify this x with that power to become power of 4. And also this constant can be dropped outside or left inside and it will be dropped. But the integration now is 4x power of 4 dx. Only x power 4. So it's a simple integration. So we have what we did before, the x power of 5 over 5 times the ln of x minus 1 over 5, and now the integration of x to the power of 4, where we will add 1 to the power and divide, right? This was I1 that we need to replace it with that integral, right? In order to have simply at the end. So here we accumulate the result. We have this integral, the ln power 2x times x power 5 over 5 minus 2 over 5, and instead of the integral of x power 4 ln x, we will plug in the result that we got here. So here the integration, the integration of x power 4 ln x power 2, which is the original function here, I'm reading here, is equal to the first part that we achieved minus 2 over 5 and open bracket in order not to mess up with the signs, and finally plus c because it's the indefinite integral. It's a bit long and it includes like a spiral of by parts, but it's very simple. Now we have the integration of ln of the 2x plus 1. Again, under the integral we don't have any function except the ln, and this ln we don't know it's the derivative of what, so we will use it as the u. We will take it as it is. And then what about the dv? We will take the dx simply. The derivative of u, which is u dash, we can write du as we did, or u dash. The derivative of the ln of something is the 1 over that thing times the derivative of that bracket. The derivative of 2x is 2, and plus 1 of course is the 0. Now the v is the integral of the dx. The integration and the d goes together, and this is the x. And now this integral, if we called that I, the I is equal to the product of u times v minus the integration of the v du. So we have x, which is the v, times the ln of 2x plus 1, which is the u, minus the new integration where we have x times 2 times 1 over 2x plus 1. Of course, we can get the numerators together, 2x, and the denominator. In the denominator, we have 2x plus 1 dx. Now we need to integrate that new integration, which is simple. It doesn't include a ln at all, but it looks different. You remember when we had the integration of x plus 1 over x dx? This form, we said that it has a common denominator, right? The different terms in the numerator got a common denominator, and we said that we can distribute the denominator using the algebra like that over the terms, and then the x goes with the x, leaving 1 plus the 1 over x. And now if they are separated by a sum or a subtraction, a sum or difference, plus or minus, we can integrate each alone and act as a separator. The integration of 1 is x, and then the integration of 1 over x, which is x to the power of negative 1, is the ln of the absolute of x, right? Now what if we have the opposite of this? We have x over x plus 1. Wherever you see something is here and the same thing is repeated in the denominator, and the plus 1 is the extra. We need it in the numerator, not in the denominator. So they do this part. They do that trick. Plus 1 minus 1. What we did at the end? Nothing. Plus 1 and minus 1. We did nothing to the problem itself, wrote in red here. But it will enable us to rewrite that integral. Let's call it I1 in order to focus on it. Now we can rewrite I1 as the integration of 2x plus 1 over 2x plus 1 minus 1 over 2x plus 1. Now we have divided this denominator over the two parts in the numerator, and we divided them as we want in order to be able to solve it, of course, dx. Now what about the 2x plus 1 over the 2x plus 1? They will go together, simplified, leaving the 1, and we will have here the 1 over 2x plus 1, which is a bracket of no power in the denominator. We remember that we can move it up and change the power to -1, and we can now solve the integration. The integration of 1 is x, and the integration of that part, yes, that was the, if we have the function raised to the power of 1 in the denominator, we need its derivative in the numerator, right? We can multiply by 2 and divide by 2 at the same time, and here the half is the extra, and the 2 over 2x plus 1, this is a function, and its derivative is up in the numerator. So we can solve this integral. Remember that integral when we said it's equal to, when we have the f dash and f to the power of -1 dx, this was the same as the len of the absolute of f plus c. So we will say that now it's the len of the absolute of the function, which has its derivative in the numerator, which is what? The 2x plus 1. So this is the I1 that we solved now. Let's plug it in the problem. So now our integration is the first part that we achieved here. Don't forget it, that part. This is the x len 2x plus 1 from the pi parts, minus that integration that we solved now as this part, which is, we have to write it between brackets, x minus half of the len x, the len 2x plus 1, and then we close the bracket in plus c. So we have replaced that integral here, that we got its value, with that solution. This is a nice smart idea that we have to consider and learn. Now we have the part E is x to the power of 2 times len x. It's pretty much like the x to the power of 4 times len x all to the power of 2. I'll leave it for you as an exercise, and if you got any problem, refer to me or to your TA. And let's go to that part F, where we have the integration of the product x to the power of 2 plus 1. This is a function times e to the power of -x. Now we have the product again of two functions. None of them is the derivative of the other. So we have to use the by parts technique, calling one of them, one of the two products, as u. And of course we will use the x to the power of 2 plus 1 and the dv, which is e to the power of -x dx. Now the derivative of u is simply the 2x, and the integration of v is what? The integration of e to the power of -x dx. This function integration is the same, and as if we multiplied by -1 inside and divide by -1 outside. So the divide by -1 is the extra, which will drop. And then we are able to rewrite that form. U times V minus the integration of V du. So this integral, if we call that I, is U times V, which is x squared plus 1 times e to the power of negative x over -1, minus the integration of 2x times e to the power of negative x over -1 dx. Now, this new integration carries constants, the 2 and the -1. We can take these outside. So we will have the integration of, again, that first part will drop. And then we have e to the power of negative x divided -1. We can take it here in front of the term, the whole term, because all of them are the times. And then -1, take it outside to change the sign to positive, and 2 outside, so it's going to be 2, and inside the integral we have x times e to the power of negative x dx. Now inside the integration still we have the product of two functions, yes, but it's a more simple, it's pretty much simple. Here we have x power 2 plus 1, and here we have only x. So one only step is left. Let's call that I1, and I'll tell you another trick to get rid of that. So we will take I1 and we will solve it here in the draft. We will say that I1 is the integration of x times e to the power of negative x dx. So we have to call u the x and the dv as e to the power of negative x. Of course, always choose the dv as the exponential, because the derivative of x, the exponential, is very easy. We can get it simply if we have the integration of e to the power of ax plus b. We say directly that this is the integration of the e to the power of ax plus b over a, right? This is the extra which drops, as if we multiplied by a inside and times 1 over a outside. The a inside goes with the integration, but 1 over a outside drops with the solution. So the e to the power ax plus b with times a, these two together goes with the integral, and they are the derivative of the e to the power ax plus b. The 1 over a outside is the extra which drops. So this is what we do if we have the exponential. Now we can say that the v is simply the e to the power of negative x over -1, and the u dash is equal to 1. We will set the integral as u times v minus the integration of this horizontal. And this integration, the horizontal, is going to be e to the power of negative x times 1. So we are left only with the integration of e to the power of negative x, which we can solve it. So I1 is going to be equal x times e to the power of negative x over -1. We can simplify this later. Minus integration, and there is a minus here. So the minus with the minus, minus times negative is positive, and the integration is going to be e to the power of negative x times 1. So we have only e to the power of negative x dx, and this integration we can solve it simply because we know, like we did here. So we can say that this term now is a negative term plus the integration of e to the power of negative x, which is itself divided by -1. This is the I1 finally, right? So we are going to plug it here and say that our integral is that term plus 2 times, and open a bracket and write what we got from I1. We can write it minus and finally plus c. So this negative times positive turns to negative here, and finally plus c. There is a tip in the textbook say, if the u is a polynomial And every time you differentiate the u, it drops the degree by 1. So when it's x squared plus 1, the derivative is 2x. And then the derivative of 2x is 2. And then the derivative of the 2 as a constant is 0. So we can finish differentiation. I'll tell you about the tabular technique. This is a different way to solve it. So we can have another solution for the same problem using the tabular technique, where we will call the u as x power 2 plus 1 to get the benefit that its derivative is very simple and direct, and the dv as the e to the power of negative x dx, also to get the benefit that its integration, which we would need, is very simple and direct. And we can differentiate the u as 2x, and then the second derivative as 2, and then the third derivative as 0, right? And then we should set here a table. So let's have a table-like form. Okay. And then we need to integrate the dv as much as we differentiated the u. So the v here is going to be e to the power of negative x divided negative 1, right? And then the integration of the v is going to be e to the power of negative x divided by negative 1, another integral, so we will divide with negative 1 again. A second integration is going to be, or the following integration is going to be negative 1 times negative 1 times negative 1, right? And of course we can simplify this. 3 negatives multiplied will leave us with a negative, and here negative times negative, this turns into positive, and here negative divided negative 1 will leave us with e to the power of negative x. So now we can write the solution directly using that table, where we would multiply u times v. So the integral is going to be u x squared plus 1, this u times the v, which is e to the power of negative x, minus that diagonal, so minus, and that diagonal is 2x times e to the power of negative x. So we don't have a sign, so I will write 2x times e to the power of negative x. And then, so this product is with a minus, that one with the plus, and then with the minus, minus 2 times e to the power of negative x, and this was with a negative, so we can turn this into positive. And finally, we should say plus the integration of the horizontal line. But 0 times anything is 0, and therefore the integration of the 0 is, remember the integration of the 0, like any constant, is c, right? The derivative of any number was 0, and therefore the integration of the 0 is the constant. And remember as well, if we have the integration of any constant, it's only that constant times x, right? Like we say the integration of 3. Remember, the 3 is the derivative of what? Of 3x, right? So we say the 3x and then plus the integration constant, we can call it k now, like we do when we have a cost function. Okay, so here we are going to write plus c. You can use this if you find it easier. You can use the other technique using spiral of by parts, several by parts. But take care of choosing the u. The u is always chosen as the function which is easier to differentiate. So we always choose the u as the polynomial when it's multiplied by exponential. Exponential is with the least priority, and the logarithmic is with the highest priority. So whenever we see the len of anything inside the integration, the len multiplied by x to the power of 2, multiplied by x to the power of 4, multiplied even with the exponential, we are going to choose it as u, because we are unable to integrate it except using by parts. So we have to play it smart and choose the u always as the polynomial if it exists, x to the power of 2, x to the power of 3, even square root of x, we will use it as u. And if we have the len, we will choose the len instead as the u. If we have the exponential times anything, we will use the exponential as the dv, because as you see, the integration of the exponential is always forward and straight and positive. Now let's move to exercise 2, which discuss the definite integrals. So the definite integral versus the indefinite integral. In the definite integral, instead of integrating this stretched s, we said that it's for the sum, but with the stretched s. This stretched s without numbers, it's going to include a lower limit and an upper limit. So the integration from a to b for f of x dx. And because we are integrating with respect to x, so the a and the b are x's, as if the a is the x1 that we are integrating from x1 up till x2, up till start till the end, or the lower limit to the upper limit. And this integration got a graphical interpretation or a graphical meaning, which means it's giving us the area under the f of x curve from x equal a to x equal b. This area denoted by a, from a to b, versus the indefinite integral, which gave us the average area under the curve f of x. What we will do in the definite integral, simply we will get the antiderivative exactly like we did with the indefinite integral. We will use the same rules, but instead of here it was the same rules that we used in terms of x, and then we add plus c, that was the solution, a function, right, in x. But here in the definite, we are going to get the antiderivative, and then we will substitute. We will get f of x as we did, but we will substitute with b and then subtract from it the substitution of a. And if we added plus c here, we will have the f, and instead of x, we will substitute it by b plus c, and then minus the f capital of b we have a bracket here plus c, right? So if we distributed this negative to these two terms, we will have simply f of b minus f of a. And this is going to be a number, of course. So the solution of the definite integral is a number which represent the area under the curve from x equal a to x equal b, and its solution is a number, like we will do now. It has several properties, and it solves many problems in mathematics. So let's get the first one here. This is a simple integration of the 2x from x equals 0 to 1. So what we are going to do here is like we did before. So we will integrate the 2x. Of course, the 2 is a constant. We can leave it outside the integration, and we are only integrating the x. So this integral is equal to 2, and the integration of x, which is x to the power of 2 over 2. Now we will substitute the x once with the 1 and another time with the 0. So we can write it here as if we are writing it as a power and or upward in that position, or and the 0 as a sub. So we have the 2 outside. I'll substitute the x with the 1 over 2 minus, instead of the x, then we will have the 0, the lower limit, over 2. And then solving this, here we have 1/2 minus 0. 0 divided anything is 0 times 2. So this is going to be equals to 1. Very good. So what we did, nothing more than the substitution we do at the end in the problems. let's take part B. It's that famous part that we know how to solve it. We have here one denominator and several terms in the numerator. So we recall that if we have a plus b minus c all is over d, we will rewrite this as, or we are able to rewrite it as a over d plus b over c minus, plus b over d minus c over d. So these two expressions are equivalent and equal. We may use any of them according to our problem. So here, of course, we need to have a more simple power of x in order to be able to integrate it. So inside the integration, and for the meantime, we will forget about the boundaries, the 1 and 4. And we will go with the integration, but we will copy them with the symbol of the integration. So we can say that we have now 2x over square root of x, and this is an integral minus the integration, again from 1 to 4, of the 1 over square root of x dx. Now we have two separate integrals. We don't have to write it like this, but just we are discussing it now. We know that if we have an x in the numerator and x in the denominator, we can also simplify this. Whatever the power is, we can write them into 1x and we subtract the power. So we can say that this integral turns into 1 from 1 to 4, and it turns to x. The upward x here is to the power of 1, and the x in the denominator is the square root, which is equivalent to x to the power of half. So 1 minus half is 1/2, so we have here x to the power of 1/2. This 2 can go outside the integration because it's a constant. We will not integrate it. And then minus the integration of 1 over square root of x. Square root of x is x to the power of half. And if we have 1 over x, this is equivalent to x to the power of -1, so we move it to x to the power of -1/2 dx. And now it turns to a simple power of x, and its integration is very simple as if the power is not -1, so we add 1. Half plus 1 is the 3 over 2, and we can divide by 3 over 2 or multiply with the reciprocal directly here, and then minus x to the power of -1/2 plus 1. This is 1/2. We can write it like this, or over 1/2, or multiply it with 2, right? Now, instead of adding the c, the integral constant, we will substitute by x equal 4 first, and then minus subtract by x equals 1. So we have here 2 times 2 over 3, this is 4 over 3, and the x is going to be 4 to the power of 3 over 2, minus this divide by half. If you wrote 1 over half in the calculator, you will get 2, and the x, which is 4 now, raised to the power of half. Now we need to subtract from that, all of this, we need to subtract by substituting x with the 1. So we have 4 over 3, and the 1 to the power of 3 over 2, and then minus 2 times 1 to the power of 1/2. Of course, 1 to any power is 1 to the powers that we have here, positive power. So it's going to be 1, and then we can solve this and get the value of the result. There are several online integral calculators which we can use. This is one of them. It's called the Integral Dash Calculator. It's very good if you need to double check your solution, and it provides steps as well. So here we have 2x minus 1 over the square root of x. This is for your life in general, not just for using this website, for this course, I mean. 2x minus 1, and then over the square root of x. This is how we can see. We can add our boundaries as well. which we had, it was 1 and 4. So we have from 1 to 4, and we say go. And then we have the solution displayed here. This is the solution. Show steps, it will show you the steps. And this is the final solution. Of course, we don't add C when we substitute. Here, let's say that the final solution is going to be 22 by 3, approximated to the 7.3. If we need to show the steps here, it can show us the steps. It might use different method, of course, but it can guide you sometimes. And also, if you have a different solution and you need to check it, you can check here, compare this expression to your own answer. So if you get a different expression, you can write it here, and then you will be able, it will be able to compare it with the solution and tell you if it's equivalent or not. Because of course, you know that algebraically we have several things. We can have different shapes for the same algebraic expressions. So expression here we have the 22 by. So now let's consider the integration with the absolute function. If we have here the integration of the absolute of 2x minus 3, we know that the absolute of x was by definition equal either to x or negative x. It output x if x is bigger than or equal 0, and negative x if x is negative, less than 0. And the same with any absolute function. So the absolute of 2x minus 3 is equal either to 2x minus 3 or 2x minus 3 multiplied with negative, right? This happens if around the vertex. Here the vertex was 0. What we do, we take what's inside the absolute, which is 2x minus 3, and we can equate it by 0. Equating this by 0, the x is going to be what? 3 over 2. We take the 3 outside and then divide by 2. So here it's going to be positive when x is bigger than or equal to 3 over 2, and negative when x is less than the 3 over 2. Okay, now let's see that this function varies between the 3 over 2, around the 3 over 2, from negative infinity to 3 over 2. This means when x is less than 3 over 2, the function appears with the negative sign. So the output of the absolute is negative the function. And from 3 over 2 to infinity, the function outputs 2x minus 3. Now let's get back to the integral. The integration here is from 0 to 3. The 0 is to the left of the 3 over 2. And the 3, we know that the 3 over 2 is 1.5. So the 3 is to the right of the 3 over 2. And therefore, the integral crosses the vertex. At that time, we have to use the property which says the integration from a to b for f, any function, dx, can be rewritten as the integration the same from a to c plus from c to b. Now, as if we divided the integration in between the c. This happens if c is between a and b, and if f is continuous function. And we will always have this case. Here, we can divide this integral from 0 to 3. I will write the integral itself of the absolute function. We will divide it into an integration from 0 to 3 over 2. Why? Because from 0 to 3 over 2, the function, the absolute of 2x minus 3 is going to be the negative, and now we solved the absolute. In addition to from 3 over 2 till 3, the last part, and in this interval from 3 over 2 to 3, the absolute of 2x minus 3 is simply output as 2x minus 3. Now we solved the absolute and we divided our integral according to the boundaries, so we can now solve the integration. The negative as if it's a number or a constant, it drops, and the integration of 2 times x, the 2 drops, and the x integration is x power 2 over 2 minus 3. 3 is derivative of what? Of 3x. And we will substitute the x with the 3 over 2 minus substituting it with the 0, which cancels, of course, plus the integral of the 2x now minus 3. We can integrate each alone. 2x, 2, the 2 drops, and the x integral is x power 2 over 2. Again, the 3 integral is minus 3x, and we will here substitute by the 3 first and subtract, substituting the x by the 3 over 2. And therefore, we can simplify this, of course, to simplify this 2 with that one here and there. And then we will have the negative, and instead of the x, we have the 3 over 2 squared, right? Minus 3 times 3 over 2. And then from this, we can put a bigger bracket here, subtract the 0. And of course, we have the 0 power 2 and minus 3 times 0, that's 0. And then plus the other function, we need a big bracket and substitute the x with the 3. So we're going to have 3 squared minus 3 times 3. And this is going to be minus substituting the x with the 3 over 2. So we have the 3 over 2 squared, and this is another bracket, minus the 3 times 3 over 2. Whenever you see sign, always use a bracket in order not to miss the sign. So this bracket carries that end. That bracket ends here, right? And then this bracket ends here. Okay, that one is that one here. And then simply that one, I'll make it an upward arrow, is that one close. So we substitute by the 3 over 2, and then we substitute by the 0, plus we substitute here with the 3, minus the substitute with the 3 over 2 and take care of the sign. And then you will evaluate the number by the calculator, or you may use the calculator to solve the integral itself. So here in your regular Casio calculators, we have this button. We have this button, right? And we might use the absolute. Where is the absolute function? Yes, here it is, with the shift. And then the absolute. Inside we need the 2. And then we have the x, alpha x, minus 3. And then we may use these arrows in order to go to the boundaries. 0. We only use this in order to make sure of the number that we calculated. This is 9 over 2. Then we write here that this is equal to 9 over 2. But you have to show all this working out of the problem, and that you substituted the upper bound minus the substitution with the lower bound in each integral. Only the last number we can commute it with the like we did now. Okay. Let's get to part D, where we have the integral of ln x divided by x to the power of 2. And of course, we would think about the function first with the basic formula. So none of them is the derivative of the other, so we have to use by parts. And we know that this integral from 1 to 2, it carries the ln of x, and then we can say that it's multiplied with x to the power of negative 2 dx, right? We can take that x to the power of 2 upwards in order to see it correctly with its power. And then now we are able to choose between the u and the dv, we know that the u will always be chosen as the ln of x, and the dv, because it's of the highest priority, right? We can choose anything else beside the ln x as the dv. And then what we do here, we differentiate the u and we integrate the dv to become v, with integrating the x to the power of 2 dx. First, let's differentiate the ln x, which is 1 over x dx. We can write it u dash, like we did before. And here the integration, this is a simple power rule where the power is not -1, so we will add 1 to become -1 over -1. And then we will rewrite that. We will have the integration of this product first, which is negative x to the power of -1 times the ln x. As we said, we always write anything multiplied with the ln to its left in order not to mess it up and take it inside the ln with the x, minus, and we have here minus, so it will turn to plus. The integration is going to be x to the power of -1 times 1 over x, which is again x to the power of -1 dx. So we can combine these together. So we have now negative x to the power of -1 ln x, fine, plus the integration of x. Here, this one is the power of -1, x to the power of -1 times x to the power of -1. Yes, we combine them into one power and we add into one base and we add the power. And now it turns to a simple integration. This is the first part. And the integration of x to the power of -2, because the power is not -1, so we add 1. -2 plus 1 is -1 over -1. And now, instead of adding the integral constant, we have boundaries, right? So all of this integration was from 1 to 2. And then here we will substitute by 2 and 1. 2 first and then 1. So we have 2 to the power of -1 times the ln of the 2 plus 2 to the power of -1 over -1, right? And then we subtract what? By the 1. We have x and minus and 1 to the power of -1, and then ln 1. We know that ln 1 is 0, right? So we don't have to write it. 1 to the power of -1 over -1, and we close this. Always we know that ln 1 is 0, and therefore all of this goes minus 1. This is going to be the left part. And finally, we will have this approximately 0.1534. So this is going to be the final solution. This is a decimal point. Okay, so this is our final solution for this problem. Let's move to another exercise. We have here the square root of x times ln x. Let's do it. Here. So here again we have the ln x multiplied by another function. So what we do here, we know that none of them is the derivative of the other. So we go directly in using the by parts. We need to choose u and dv, because this is integration is going to turn into uv minus the integration of v du. Now the u is the ln x, we have no other option. The dv is the root x, which we can write it as x to the power of half directly, dx. Now here we differentiate and here we integrate. So the differentiation of u is 1 over x dx, and the integration of v, this is simply a power rule. The power is not -1, so half plus 1 is the 3 over 2 over the 3 over 2, or we can write it 2 over 3 directly, because 1 over 3 over 2 is the 2 over 3, right? And then we will rewrite as u times v minus the integration of the horizontal bar. So the integral is 2 over 3 x to the power 3 over 2 times ln x, fine, minus the integration of these products. 2 over 3 is a constant, we can drop it outside the integral, and then 1 over x times x to the power 3 over 2 dx. Now we have x and x. Of course, we will combine this before going in the integration. So we will rewrite this as 2 over 3 and x to the power of 3 over 2 ln x. This is the first part, minus 2 over 3. This is the constant outside. And inside the integral, we have x to the power 3 over 2 minus 1, which is x to the power of half dx. And this is a simple power integral. I will copy that part quickly. And then x is going to be to the power of half, because this power is not negative 1. So we add 1 to the half to become 1 and half, or 3 over 2. Don't forget to divide by the new power. And instead of writing the integral constant here, we will substitute with 4 first and then minus substituting the x by 1. So here we are going to have the 2 over 3 and then the x, which is 4. Sorry. Power 3 over 2. And then ln 4 minus again 2 over 3, the 4 instead of the x, to the power 3 over 2 over the 3 over 2. All of this is the expression, and substituting the x by 4. And then we subtract with substituting the x by 1. So we have 2 over 3 and 1 to the power of 3 over 2. The ln 1 is 0, so this term is 0. And then minus 2 over 3, this is going to be 4 over 9. This 2 over 3 divided 3 over 2. This bar is a divide, right? 2 over 3 divided 3 over 2 is 4 over 9. And then the x, which is the 1 to the power 3 over 2, this x is going to be 1 as it is. And then we subtract, and we get the final solution. The final solution here is approximately 4.2824. This is the final solution. Very good. Now I want to give you some notes about the definite integral. If we are integrating from a to a, from a point to the same point, f dx, of course we said that the definite integral represents the area in the graphical perspective, the area under the f of x from a to b, from x equals a to x equals b, right? If I said that we need to integrate from a to a, so it means that we need the area from a to a. Whatever the function is, of course, this integral is going to be 0. Also, if we want to integrate from a to b, and we need to switch these limits, we can do this, yes, but we will add a sign. So this integral is equivalent to the integration from b to a, but the negative, from b to a to the same f dx. So as if when we calculate the area from a to b, it's going to be exactly the same from b to a, but to indicate the different signs, we add this negative. Like when we integrate from a to b, any k constant times f of x dx, we can take the constant outside the integration because it's not integrated, and we integrate the function of x. Finally, if we are integrating from a to b and for f of x dx, you remember the even and odd function? If we have an even function, we said that we will have the same shape around the y-axis, right? If we are integrating from, let's say, negative a to a, from negative a to a, and this function is even, so what's here, it's the same there. So we can rewrite this as 2, and the integration turns from 0 to a, f of x dx. This always happens if this f is even function. And even function means that f of negative x is equal to f of x. We will have some problems over this part in the next worksheet, but let's just indicate it now. What if this function is odd? So if this f is an odd function, which means that f of negative x is equal to the negative f of x. It also means that if we're having a graph, what we have here, we do have, but here, right? So if we're integrating from negative a to a, this area is going to cancel that area. And therefore, we will say that the integration, this integration from negative a to a for that f, if it's odd, is equal to what? 0. Directly is equal to 0. So if you thought that the function inside the integral is odd, you may try this test to show that it's odd and make sure for yourself, of course. And then you can directly say that this integral is 0. We will return back to this idea and that concept in the next worksheet. Don't worry. Now let's take that integral of a simple one, e to the power 3x plus 2. Yes, this pretty much looks like the e to the power ax plus b, right? And inside the integration and then dx. We know that what we need here was the derivative of the numerator. And the derivative of the numerator is only a. So we multiply by a and divide by a outside, and therefore 1 over a is the extra which drops, and e to the power of the function is the result plus c, right? So this is what we are going to do here. We will say that the integral is e to the power of the function, and then we divide by the extra. Instead of adding the integral constant, we will substitute with 1 and 0, and therefore we can leave the 1 over 3 outside because it's a constant, and substitute the x by 1 plus 2 minus e, and substitute the x by 0 plus 2, and then we have here 1 over 3, and e to the power of 3 plus 2, this is e to the power of 5. And don't miss that e to the power of 0 is 1, okay? E to the power of 0 is not 0 if you're substituting with 0, but here we have 3 times 0 plus 2, which is e to the power of 2. And you may leave it like this, because if we want its equivalent, it's going to be a decimal, right? This solution is going to be a decimal, and we can leave it like this. Let's consider another problem here. I want to show you something. If we are integrating, now this integral I want to consider with you to show you something. If we have the absolute of 2x over 1 plus x squared, of course we have to solve the absolute first. And let's take it outside. The absolute of 2x, this is going to give us either 2x or negative 2x, right? And it's going to give us this at the vertex. We say that 2x equals 0. We will divide by 2 both sides to get x equal 0. So this positive is going to happen when x is bigger than or equal to 0, and the negative when x is less than 0. Now let's translate this from 0 to infinity. When x is bigger than 0, the function is 2x. From negative infinity to 0, in this interval, when x is less than 0, the function is negative 2x. What about the integration here? The integration wants to study from negative 2, which is of course to the left of the 0, to negative 1. Both of the limits are to the left of the 0. So we don't need to divide the integral. We will directly integrate it into one step from negative 2 to negative 1, and we will substitute the absolute of 2x with the negative 2x, because we are in the interval where the function is negative, where the absolute is negative. And then 1 plus x squared dx. Now we can figure out that we have here in the denominator 1 plus x squared, and yes, the other function, we think about this as a bracket and that as another bracket. If we called the lower bracket f, then its f dash is what? Derivative of 1 is 0 and x is 2x. Yes, it's upward here. And the negative, as if it's a constant extra, we can take it outside the integral. And we will have negative the integration of f dash, which is 2x, over f, which is 1 plus x squared dx from negative 2 to negative 1. This integral was equivalent to the len, right? So we have here negative len of the absolute of the function plus c. What's inside the absolute is the function which we used to get its derivative. You don't have to return back to the problem. 1 plus x squared, and instead of plus c, oh I missed that, instead of plus c we will direct substitute. Here we can put a bar or this bracket. We will directly substitute from negative 2 to negative 1. Of course, we substitute by negative 1 first. Negative 1 squared is 1, so we have the negative of the len 2, and then minus negative 2 squared is 4 plus 1. This is the len 5. Right? So we can leave it like this, as if it's len 5 minus the ln of 2. Of course, this will have an equivalent decimal. I've made it with that calculator, which is 0.9. We can leave it as 0.92. So we will approximate into 2 decimal places if you want to write it in the decimal form. So the absolute, we don't have always to divide the integral. Sometimes we will be, or the integral is going to lie in one of the 2 intervals. And then we will just write its equivalency, right? Now we came to the end of this tutorial. Thank you